Alright, so 1.3 calculus, this is basically going to do a full year of trig in a few weeks. So we're just going to kind of recap, not every single thing we did in trig, but pretty much the stuff that we did in trig that's going to still matter to calculus life. So one thing we used to do in trig is turn degrees, like this, into radians, these pi things. Does anybody remember how to turn a degree value into a radian value?
Multiply pi over 180.
That is correct. We would look to multiply by a fraction with pi over 180. Because pi and 180 really are the same. So in effect, if you have a top and a bottom of a fraction that are the same, that fraction is equivalent to 1. And if you multiply by 1, that keeps things the same. It just makes them look different. It's kind of like a trig version of, if I want a different fraction than 2/3, I can multiply by 4/4 and get like 8/12. I multiplied by 1, I made it look different, but I didn't change it really, I just made it look different. Maybe I needed a common denominator to do something. That's what's going on with this. We're basically trying to cancel the degrees by getting the degree value on the bottom, and it'll create some pi. So we do that, get our nice little cancel going, a new fraction pi friend, this would have a pi. I'm talking with them. Question about that? Are we good? To get from radians to degrees, we can have a plan A, or we can have a plan B. Both plans are equally good. Anybody have a plan to get from radians to degrees?
Replace pi with 180.
Yep. One thing we can do is just replace the pi by a 180. This pi is the same as 180. Stick that in, math it, and we get 30. Or we can take an approach similar to this. How could we use that idea in rewind mode? We can multiply by 180 over pi. Because if you're multiplying moving forward, you could divide your way back. Dividing a fraction just involves a flip. So the homework will have a little bit of that in it. Question about those conversions. A second reminder, today's trig lesson will be about angles in standard position and finding reference angles. Does anybody remember anything about measuring angles in standard position? What numbers are where and such?
Oh, is it like 360 minus in the bottom left?
Where is 0 on this?
Oh.
Like
And that's 0.
90.
90.
Oh, that's
180.
180.
I was going a little too
70.
360.
We're getting ahead of myself.
We did another system of measurement last year. Do you remember what it was called? Bearing, correct. Where did that put the 0?
Up.
Up. And then 90 was
Over there.
went the other way.
Okay.
Bearing is dead. There is no bearing in calculus.
Yes,
Bearing is out. Everything will just be standard position. That's the good news. The bad news is degrees are also basically dead. Everything will basically be in radians. So you may choose to do the switch back and forths. I think you guys, like most people, seem more comfortable with degrees than radians. So if radians make you uncomfortable, then this will be a kind of a key feature of your year. Change your radians to degrees, deal with them. Maybe you have to switch them back, maybe you don't. But either you'll want to get growingly more comfortable with radians, or you're going to be doing the swapsies with them. That's sort of kind of like up to you. If I'm talking about reference angles, like if I head to a position like this, what does it mean to find a reference angle?
Go to the x-axis.
Go to the x-axis. So this would be a reference angle. reference angles always touch the x, and they're also always acute. So like if I'm over there, that's the reference angle. If I'm here, that's a reference angle. If I'm here, that's a reference angle. The reference angles touch the x and they're question about that. Okay. Sine got invented to you. It'll get invented to the trig class in their next lesson after today. So almost a year ago in your life. What was sine? O over H. Based on a right triangle, where someone chose an angle for you, what was the name of this side? O
Yes.
for
Opposite.
opposite. This is
Adjacent.
A for adjacent.
H.
That's H for
Hypotenuse.
what? Cosine? Tan?
Over.
Who was sine's friend when we went upside down? Cosecant. Cosine's friend
Secant.
and tangent's friend. That's good. That all seems like that's still in there somewhere.
Geo.
The power of 2. Hello, Amelia. Hope you're enjoying your vacation. Having a third brain is always nice too when we start doing these open-ended. I just asked you what you remembered lessons here in the beginning of the calculus class.
Is that like 360 minus 180 minus 180 plus things still alive or not? Is that
Nah, that's not really going to matter to you. That was like a vector. It was a vector-specific process. I think you had a program that was even doing stuff like that at one point. That was like, yeah, that's dead to us. Question about the right edge of the board before we move left. You can pause it while you move.
We're good.
All right. So we learned the last thing we learned that was part of trig in the blue book trig stuff, chapter 3, was the thing about trig identities. We had like reciprocal properties and quotient properties and double angles and half angles. There was 35 of them eventually that we learned. There's a handful of those that matter to our life. I would say the Pythagorean 3 identities have lived forward with us. Do you remember any of the 3 Pythagorean identities?
sine squared plus cosine squared equals 1?
That's true. And they all kind of take that form. They involve squares and ones and adds, but sometimes the 1 isn't over here all the time.
Is the one that's like 1 plus cosine squared? Sine squared? Tan
I think I'm actually right.
squared. Equals secant squared.
Yeah.
Good.
1 plus cosecant squared, or cotan squared equals cosecant squared.
Those are the only 3 I think I'm going to drop on you for now, because that's the only 3 that really matter, I think, in this homework. There will be times later in the year that some other ones will crop up. I think some of the double angles sneak out in like the last chapter of the year, but it's no point in throwing those in those now, because that's really like far away. You guys that have some of the books that have been handed down through the generations, inside the front cover, there's a lot of these facts, I think. Like, there's a little, like, trig notes summary that starts the book with some good, potentially good stuff in there, depending on who had your book before. The chart is still a superstar. So, I'll splotch you the sine, cosine, tangent, headings. What were the numbers here?
0,
0.
30, 45, 69.
For calculus purposes, since we're very radian based, I would suggest having a radian column as well as a degree column in our charts. We did 60 earlier this period as part of 3. And we did 30 earlier this year, it was pi over 6. Those were in our sample problems over there. 0 would obviously be 0. 45? 490?
Pi over 4 and pi over 2.
Pi over 4, pi over 2. Do you remember how the sign answers went?
Ooh. 0.
Yeah.
1/2.
Yeah.
Oh.
Root 2.
Root 2 over 2.
Yeah.
Root 3 over 2.
Yeah.
1.
Right. One weird pattern that's like sort of concealed, it counts roots all over 2. The root of 0 over 2, let's simplify. The root of 1 over 2. The root of 2 over 2 stands. Root of 3 over 2 stands. Root of 4 over 2 can simplify. Maybe that pattern helps you, maybe it doesn't, I don't know. If you got sine, you got cosine, because you just
Flip it upside down.
wrote them upside down. Same numbers, reverse order. You remember a way that you can always make tan if you forget it?
Sine over cosine.
Sine dividing cosine. Sine dividing cosine makes tan. So when 0 divides anything,
Which is 0.
0. When anything divides 0,
Possible.
possible. When anything divides itself,
Is
is 1. This one?
Wait, which one did you went to? Is it that one?
Now you have to do roots on the bottom type stuff. Root 3 over 3.
Yeah, in our history, we could think about dividing this and getting a cancel of the 2's. If 1 divides root 3, we've always fixed that to go root 3 over 3. I don't remember if it's today's lesson. I know some lesson in the book, they're actually okay sometimes with roots on the bottom. So if you go, I would still prefer the root 3 over 3 because that's just what we're used to. But if you look in the back of the book and it has 1 over root 3 and they didn't fix it, that's okay too. I'm not going to argue about that on homework. On a test, I'd rather you fix it. But on homework, like, hey, whatever, if you want to just do it the way they're doing it, I can't complain about that. So this, you might see a 1 over root 2 sometimes on these in this book. And this, you might see a 1 over root 3 on that in our one. How about this one?
Root 3.
That's just going to be root 3. The only ones with differences of opinions from time to time might be these. To be 1 over root 2's and 1 over root 3's. But again, homework, I don't care. Test, let's do it the way we're used to doing it. We'll do some samples on that because that's going to maybe need a little bit of practice beyond just giving you the background. It is worth dropping you a mention. We did a bunch of trig graphing. There's a minimal amount of trig graphing in this year, but if you ever are trying to remember how to do like a sine graph or a cosine graph, you can either utilize page 26 or just graph that on your calculator if you remember how to graph on the calculator. And we did that yesterday, right? Graphed on the calculator a little bit? Yeah. I did that with you guys and with trig. Sometimes I get my day. I know I did it yesterday, but I'm like, who did I do that with?
Yeah.
Both, actually, I think. Question about background information, what this is like covering. That's 95% of the trig that'll matter this year. There's another like 5%, we'll hit it a little closer to when it matters, because if I remind you on day 1 and we don't use it until day 160, that's just, I might just well not even bother probably. Let's look at homework page together. We'll drop a few more hints your way, and I'll see what I need to make up a practice problem for. So we're on page 29. We probably do either number 1 or number 2, I would guess. Syllabus says 1. Okay, so you can just check that as an odd yourself at home. That's just turning degrees into radians. I already provided a practice problem with that. We seemed like we were good, so we're probably good there. Then I probably did 3.
Yep.
Yep, so 3 is turning radians back to degrees. We did a problem already like that, so you're probably good. I'm guessing then we cut down to 9 and 10?
Yes.
Okay, so let me make up a problem like 9 or 10 because I didn't do anything quite like that yesterday. 9 and 10 are based off the chart, which there's one more bit of the chart of what's positive where that I should have probably dropped up there. Sine only, all things, cosine only, tangent only. So the homework on 9 and 10 is going to ask you to do all 6 answers for some different things. So let me pick one that they didn't do. I'll go 7 pi over 4. Might have to scroll a little bit to the right. So 7 pi over 4, your first challenge is figuring out where is that? And calculus is, again, like I said a few minutes ago, it's all radian based. So maybe you want to think about 0 and pi. And pi over 2, and 3 pi over 2, and 2 pi. But realistically, those are the only ones that really, truly matter for reference angles, because reference angles always touch the x-axis. So we're always going to be using those x-axis numbers. We never really care that much about the y-axis numbers particularly. Can you tell me which quadrant the 7 pi over 4 would be?
That is C.
It is in the C. That took a little while though, so maybe you don't want to do that. So if you want to think about radians, you could think this is like 1 3/4 pi.
Okay.
7/4, 1 3/4 pi. 1 3/4 is awfully close to 2. Definitely closer to 2 pi than it is to 1 pi. We're somewhere in here. So we're in that quadrant trying to figure out 7 pi over 4. And we want to figure out what the reference angle is. How do we figure out what the reference angle is with those?
Would it be the difference?
We do the difference. So we go 2 pi minus that. This is like it's over 1, but you want it to be over 4. So that turns into 8. Subtract, and that's pi over 4. I'll give you a plan B. This is plan A. Plan A, living with radians. You have to be good at fractions and like fractions. Pi over 4 is what we came up with, so now we just grab our answers. Sine is root 2 over 2. Cosine is root 2 over 2. Tan is 1, and that's mostly right. I'll pause there. Question about how I pulled those. Anybody with an insight as to why I can only say that's mostly right? It would be 1 full point and 2 half points on a test.
Doesn't matter where it's on the graph, like negative stuff.
Some of those are negative. We went into the cosine quadrant. So cosine is positive. Those are negative. That's plan A. Plan B. It'll get us all the same answer. Uh-oh, radians. I hate them. Replace pi with 180. 180 dividing 4, use your calculator if you need to. Multiply by 7, use your calculator if you need to. We could exchange 7 pi over 4 for 350. In the 360, 270 world, 315. More clearly in the C quadrant maybe with numbers than it was thinking about where 7 pi over 4 was going to go. But we still landed in quadrant 4. We still have to subtract these numbers. We're coming up with 45. Pi over 4 is 45. The only difference when we go looking at the chart, you're just skimming a different column. But those would lead you to the same answers and the same negativity from the same quadrant. So you pick. If you're fraction comfortable, maybe you're better to just live with the fractions and think about the pies. If fractions make you at all uncomfortable, then go ahead and convert. Deal with the degrees that makes you more comfortable. It's all going to go to the same place.
You don't have to worry about like cosec and secant.
It depends on if they ask you for all 6. So if they did, you know, for cosecant and secant, we'll just put them upside down. They keep their signs. The homework, so it looks like it wants all 6. And then if they're fixing the roots on the bottom, so should you. If they're not, then you do what you want. Fix it if you're used to it, skip it if you're not. It doesn't matter to me in the homework. Is that okay? Any uncertainty there? 9, 10, what that's about. 11 to 14, we're going to graph these but using the calculator. So what I would suggest you do is, for like number 11, graph just, even though it's not the question for 11, graph y equals sine x, then graph in the second slot y equals 2 sine x. And on your homework answer paper, just write down what the 2 did. Made it twice as wide, made it twice as tall, moved it up 2, moved it down 2. I would encourage you to guess what you're expecting before you even do it. Maybe from your trig days, you remember words like periods and amplitudes and phase displacements and vertical displacements.
What zoom do we want?
Probably zoom trig. So go like y1 equals sine x, y2 equals 2 sine x, hit graph, zoom trig if it looks wonky, and then just write down, it did this. If you need to use like little words like it got twice as wide or whatever, that's fine. If you remember the actual technical trig words from like we had frequencies and periods and that stuff, use those words too. But you don't need to make a graph on paper, just make a note like this happened. So that'll take you 11 to 18. 11 to 14 is all sine based, 15 to 18 is cosine based. Then, where does it go from there? To the 30s probably? Do we do anything through that?
33 to 34.
So from 18 we skip to 33, 34?
Yes.
Okay, so let me do, they want you to verify these identities. So they have you verifying those 2. So I'll show you how I verify the other one that's not in your homework. So let me clear this. If I wanted to prove to you that sine squared plus cosine squared makes 1, I start with the sine squared plus cosine squared part because, like, there's stuff there that we can play with. Because what do you know that sine is? What is sine? Over h. Cosine is? I can make that algebra a little bit better looking. If I want to add those, I can, because I have a and then if I think about the reality of the situation, O squared plus A squared, O squared plus A squared has to make what? Pythagorean theorem says, like a squared plus b squared equals c squared kind of stuff. O squared plus a squared is h squared. So this is h squared on top of h squared, which is 1. And that's what we were trying to show, that it would equal 1. By playing Oscar Had a Heap of Apples games and a little bit of cleaning up when we can, and reliance on this picture and the Pythagorean theorem, it just works. The other 2 can be done the same way. They're a little bit messier, not like radically, but it's based on O's, A's, H's, and it'll all boil down to this picture because they were called Pythagorean properties for a reason, because they're based on the Pythagorean theorem. I think that's where the homework cuts then, right? Is that 34? Okay, so welcome back to Trig. I don't know if Trig review from 1 year ago is more or less comfortable than algebra reviews from 1, 2, and 3 years ago, but it is what it is.